Let's see if we could do a couple of more of these conic section identification problems. So I have this problem, x squared plus y squared minus 2x plus 4y is equal to 4. And so the first thing I like to do is just try to figure out what type of conic section this will be. And we have our, this is my x squared term, my y squared term. They're on the same side of the equation, and they both have positive coefficients. So this tells me that we're going to be dealing with an ellipse. And in this case in particular, their coefficients are the same number. They're both positive 1. So this is going to tell me that this is a circle. So let's get this into standard form and try to graph this circle. So we're going to want to complete the square. So let's take the x squared, the x terms, and so we get x squared minus 2x plus something to complete the square later on. Plus, now just do the y squared terms, y squared plus 4y plus something is equal to 4. And now what do we add here? We take half of the minus 2, minus 1, square it, that becomes plus 1, add a 1. We have nothing out here, so we really just added a 1 to the left-hand side of this equation. So we have to add 1 to the right-hand side. And here, we take half of 4. Half of 4 is 2. 2 squared is 4. Put a 4 here. So you have to add a 4 to the right-hand side as well. And we actually did add just a 4 because there's nothing multiplying the 4 out here. And so this becomes x minus 1 squared plus y plus 2 squared is equal to 4 plus 1 plus 4 is equal to 9. And there you have it. We have it in the standard form of a circle. You remember that if a circle is centered at 0, the standard form would be x squared plus y squared is equal to r squared. So this is r squared. This is the radius squared. So that tells us the radius of the circle is 3. And it was just shifted so that its origin, instead of being at 0, 0, is at the point 1 minus 2. And the reason why we got 1 minus 2, we just have to think about what makes this whole expression equal 0. In this case, it was the origin. In this case, it's x equals 1. And what makes this whole expression equal 0? In this case, it was y is equal to 0. In this case, it's y is equal to minus 2. So that's our center. That's our radius. And we're ready to graph this circle. So it's at, let me see. It is at, I should graph the circle first. Oh, that's fair enough. If I, actually, why don't I just graph the circle? So it's going to be at 1 minus 2. So 1 minus 2, so it's going to be like down here. So this, it's going to come out. This circle is going to start there. As center, let's try my best, is going to be at 1, and then you go 1, 2. And so that's pretty close to its center. Maybe I should do 1, 2. That's its center, right there at 1 minus 2. And then its radius is 3. So this distance right here is 3 in any direction. It's 3, and that is 3. Fair enough. That was a pretty straightforward problem. Circles, in some ways, are the simplest. And remember, I said it's going to be an ellipse, and you say, "Oh, this isn't the standard formula for an ellipse." But just as a refresher, if you divide both sides of this equation by 9, what do you get? You get x minus 1 squared over 9 plus y plus 2 squared over 9 is equal to 1. And then you see that the horizontal axis, I guess, or I guess the horizontal diameter is going to be 3, and the horizontal radius is going to be 3, and the vertical radius is also going to be 3, because the radius never changes in this ellipse, which is really a circle. Let's do one more, just so you make sure you know this stuff cold. So I have 2x squared plus y plus 12x plus 16 is equal to 0. Let's look at the x squared and the y squared terms. There's an x squared term, but I don't see a y squared term, so this is a bit of a conundrum. And this will lead us to the fourth of our conic sections, which I talked about in the first video, but we haven't really touched on yet. That's the parabola. And how do I know it's a parabola? Well, I mean, you're familiar, and I'll go more in future videos on all the different ways that a parabola comes about, and how it's the, all the points equidistant between one point in a line and all of that. But just in very simple ways, you recognize kind of the most simple parabola is y is equal to x squared. That parabola looks something like this, right? Where its minimum point or its vertex is at the origin. Or if you have a parabola like x is equal to y squared, that looks something like this, where it's a sideways version of that one, where once again its vertex is at the origin. And just out of interest, well, actually I won't go there yet, but actually, well, no, I'll just, so we know that this is a parabola because we have a y and we have an x squared, right? They're of different degrees. There's no second degree term of the y. And just to put this in a form that's familiar to you, let's just subtract everything but the y from the left-hand side. So you get y is equal to minus 2x squared minus 12x minus 16. And this is kind of the traditional form that you're familiar with. You're probably even used to finding the zeros of this parabola, and we could do that right now. We could say, okay, when does this equation intersect the x-axis? The x-axis is when y is equal to 0. Set that equal to 0, you get minus 2x squared minus 12x minus 16. And remember, this is different than what we normally do. Normally, I would immediately break into completing the square, but I just want to figure out the zeros of this parabola first. So this is 0 is equal to minus 2 times, factoring out minus 2, you get x plus 6x plus 8. So 0 is equal to minus 2 times x plus 2 times x plus 4. I just factor that. And so for this whole thing to be 0, either this is 0 or that is 0. And so it's either x plus 2 is equal to 0 or x plus 4 is equal to 0. So x is equal to minus 2 and x is equal to minus 4. That's the two zeros of this parabola. So we immediately know one thing about this parabola, and you've probably already done this in your algebra class, is if we were to draw the x-axis, it intersects the x-axis at minus 2 and 3 and minus 4. That's all we know about this right now. So let's see if we can use some of our completing the square skills with the conic sections we've done so far to come up with a little bit more information about this parabola. So let's try to complete the square with it. I'll rewrite it down here. So it's y is equal to, this is the one I'm dealing with, and let me just take the x terms by themselves and factor out the minus 2. Minus 2 times x squared plus 6x. I'm going to add something else. And then I have a minus 16 over there. To make this a perfect square, I have to take half of this, half of the 6. Half of the 6 is 3. 3 squared is 9. If I add 9 to the right-hand side of the equation, and remember, I didn't just add 9. This 9 times minus 2 I'm adding. So if I subtract, that's minus 18. If I subtract 18 from the right-hand side, I also have to do it from the left-hand side. So subtract 18 there. And now my equation becomes y minus 18 is equal to minus 2 times, what is this? This is x plus 3 squared minus 16. And let's just get it in a form that we might start recognizing from our conic sections. Let's add 16 to both sides. So you add 16 to both sides. Y minus 18 plus 16 is going to be y minus 2, I'll put parentheses around that, is equal to minus 2 times x plus 3 squared. And now you might wonder why I put it in this form, and I did because this will help us. This is kind of the same pattern that you see with all of the other conic sections. Like if I were to tell you to graph, y is equal to x squared, y is equal to x squared, it would look something like, let me draw some axes here. Y equals x squared looks something like this. It looks like it's a parabola with the vertex at 0, or its minimum point, and that's what the vertex is the minimum point or the maximum point of the parabola. We'll talk more about that. You'll learn a lot more about that when we go into calculus, but I think you can kind of recognize it, the bottom of the U or the top of the U. If I wanted to draw y is equal to minus x squared, you could plot some points, but it looks something like that. If I were to try to graph y is equal to 2x squared, it would just be like the y is equal to x squared, but it would go up twice as fast. It would look something like that. still at the vertex at the origin. And finally, if I were to graph y is equal to minus 2x squared, it would look something like this. It would open downward and go down twice as fast. Now this equation that we ended up with right here, this is the same thing as y is equal to minus 2x squared. It has the same general shape, but instead of its vertex or its center or its kind of starting point or whatever you want to call it to be at the origin, it's shifted now. You say, what y value makes this term 0? Well, it's y is equal to 2. Just why, in this case, what y value makes this 0? Well, it's 0 here because we were at the origin. And here, what x value makes this 0 is x is equal to minus 3. So this gives us information about where the vertex is. It's at 2. It's at x is equal to minus 3, y is equal to 2. So it's at x is equal to 1, 2, 3, y is equal to 1, 2. It's right there. We already know those 2 points because we figured out it's 0. But even if we didn't know those 2 points, we know that this has the same general shape as y is equal to minus 2x squared. So it's going to open downward like this, and a little bit faster than y is equal to minus x squared. So it's going to look like this. And we know it goes through that point, and we know it goes through that point. There you go. So we've touched on every conic section, and in the next few videos I'll go into a little bit more depth of kind of the theory behind conic sections and how they came about and all of that. But I think now you're ready to tackle a lot of what you might actually see on your algebra tests. See you soon.